Hello everybody, welcome back to the Graph Algorithms course. Today we're going to talk about algorithms for exploring graphs. In particular, sort of ways to tell us sort of which vertices can be reached from which others. So, for an example of sort of the type of problem we're trying to solve here, suppose that you're playing a video game and you found the exit to some level, but you don't want to go there just yet. You want to first sort of explore this whole level, make sure you found all the secrets inside it, make sure you get all the loot and XP that there is to be found. And you can certainly wander around between the various rooms and find a bunch of passageways and so on. And you've been wandering around for a while and maybe haven't discovered anything new yet, but you'd like to make sure that you've really found everything before you leave. How do you accomplish this? How do you make sure that you found everything? And this sort of is a notion of exploring a graph. I mean, you've got these rooms, they're connected by passageways, and you want to make sure that everything, at least everything that's reachable from where you started, you can actually get to it and explore the entire region. And this is actually this and sort of related questions are actually very useful in a number of applications. For example, if you have a map and you want to find a route between, some location on the map and some other, it often depends on this sort of exploration of the graph, making sure that you can find some sequence of roads to follow to get you where you want to go. This could also be used if you're sort of building a road system and want to ensure that the entire thing is connected. You need to have some sort of algorithm to tell what can be reached from what. And finally, it has sort of more recreational things, the video game example, but also like if you want to solve a maze, this is very much can I get from the start to the finish in this sort of graph that connects things. But also various puzzles. If you think of sort of vertices as sort of possible configurations and then edges that describe moves that you can make and want to say, can I rearrange the puzzle to end up in this location? Again, this sort of exploration algorithm becomes very important. So before we get into this too much, we really want to formalize what we mean. In particular, we want to know what does it mean to be reachable from a given vertex. And basically the idea is you start at the vertex and you're allowed to follow edges of the graph and you want to be able to see what you can end up at. And so to formalize this, we define a path in a graph G to be a sequence of vertices, v0, v1, v2, etc., such that each vertex is connected to the next one by an edge of the graph. So we get some sequence of edges to follow. So the formal description of the problem that we would like to solve is, given a graph G and a vertex S in G, we'd like to find the collection of all vertices V in the graph such that there is a path from S to V, everything that we can reach from S. So just to get a little bit of practice, if we have the following graph, which vertices here are reachable from A? Well, think about it a little bit, and you find out that A, C, D, F, H, and I are all reachable. And it's easy to see that these vertices sort of do all connect up from edges, but you then can't get to B, E, G, or J. And this is sort of because there are no edges that connect any of these vertices we can reach to any of these other vertices. And so there's no way to escape except for these 6. And this is sort of the actual idea behind the algorithm. What you want to do is you want to make sure that you can actually find everything that you can reach. And so what you do is you sort of expand. You find a bunch of vertices. These are a bunch that I can reach. But then if there are any edges that connect ones that you can reach to ones that you can't reach so far, well, you have to sort of explore those edges and find the new vertices on the other end and sort of add them to the list that you know about. And you sort of keep expanding this list of vertices that you can get to until you can't connect to anything new, and then you're done. So to formalize this algorithm a little bit, we're going to keep a list of discovered nodes. And this starts out just with the vertex S that you're supposed to start at. But then what you do is, while there is an edge E that leaves this set of discovered nodes, it connects something you have discovered to something that you haven't discovered. Then what you do is you take the vertex at the other end of that edge and add it to your list of discovered nodes. And you just keep doing this until there's nothing new to be found. And then you return this list of discovered nodes. Okay, that's a reasonable algorithm and it does work. But in order to really code this up, you need to do some work to handle the bookkeeping that's required for this algorithm. You need to do things like you need to keep track of which vertices you've discovered and which edges you've dealt with, which edges you've actually checked and which ones you haven't. you also need to know sort of what order to explore new edges in. If there are several possible edges to follow, which one do you follow next? And so, what we're going to do now is we're going to talk about a specific way to implement this and deal with these sort of bookkeeping issues. The first thing that we need to do is we need to keep track of which vertices we've already found. And for this, we're going to associate a Boolean variable to each vertex, visited of v, which basically tells us, have we visited it yet? The next thing that we're going to need to do is we're going to need to, most of the vertices that we visited will have already sort of checked all of the edges relating to them. But some we haven't, and we somewhere need to keep track of a list of vertices that still have edges hanging off of them that might connect us to something new. Now, this list isn't going to appear explicitly in our program. It'll actually sort of be hidden in the program stack. So this is at points a little bit subtle, and we'll sort of see it once we introduce the algorithm. The final thing is we need to discover which order to follow new edges in. And for this, we're going to use what's known as the depth-first order. What this means is we're just sort of going to start our initial vertex, and we're going to start following a chain of edges. We're just going to follow some really long path forward until one of two things happens. One thing is we could stumble across a vertex that we've already seen before, in which case there's no reason to have followed that edge. We'll just back up to where we were before. The second thing that could happen, though, is we hit a dead end. And when we actually hit a dead end and can't go any further forward, then we actually back up. And then once we backed up, though, we don't just back all the way to the beginning. We just back up one step and then try going forwards again from that new vertex that we've found. Okay, so that's the basic idea. How do we implement this? Well, part of the beauty about this is that we have a very simple recursive algorithm. So, explore of v. The first thing you do is you set the visited marker of v to be true. We say we have visited it. Next, for each neighbor w of v, for each w that's adjacent to v, if w has not already been visited, we recursively explore w. Okay, so this is a very compact program. Let's sort of actually see what it does on an example. Oh, right. Also, I should mention that in order for this program to execute reasonably efficiently, we really want an adjacency list representation of our graph. That's because we have this for loop where we want to iterate over all of the neighbors of v in our graph. And for that, if you have an adjacency list, which gives you a list of all the neighbors of v, that's incredibly easy to do. If you don't have an adjacency list, on the other hand, this algorithm really isn't that efficient. Okay, fine. So let's look at an example. Here's a graph. We're going to start by exploring that vertex. So we mark it as visited. We then check for unvisited neighbors. And hey, look, there is one. So we recursively explore that other vertex. We mark it as visited. We search for unvisited neighbors. And we have this one. So remember, now we're sort of 3 layers into the program stack here. This is sort of a subroutine of a subroutine. But now when we're exploring this vertex, it has no unvisited neighbors. So after we've done a little bit of checking, we decide that we're done exploring this guy and we pop the stack. This other guy still, we visited both of its neighbors. We popped the stack back to the original explore call. Now, this vertex does have some unvisited neighbors left, so let's visit one of them and explore that. Mark it as visited, find an unexplored neighbor, explore that. Mark as visited, unexplored neighbor, mark as visited, unexplored neighbor. Now when we explore this vertex, though, once again, we're stuck. So we wrap up exploring that guy, pop a level up the stack, go back to exploring this other vertex, who now actually does have another unvisited neighbor, so we're going to go visit that one. Now we've actually visited everything in the graph. So all we're going to do is, at each vertex, we're going to note that all of their neighbors have been visited. We're going to pop up the stack and get back to where we started and conclude. So here we actually have found all these vertices. And in fact, if you look at it, we've actually figured out how to reach them all. If you look at sort of these darker edges, which are the ones that our algorithm sort of actually followed when we ran it, these sort of connect up to all the other vertices. And they actually tell us, if you sort of follow these edges, they give you a unique path to any other vertex that we can reach. Okay, so that's our algorithm. Let's talk about correctness. And the theorem is that if all the vertices in our graph start as unvisited, when we run explore v, it marks as visited exactly the vertices that are reachable from V. And the proof here isn't so bad. The first thing to note is that we only ever explore things that are reachable from V. And that's because, well, the way our recursive calls work are we either start at V or we explore a neighbor of a vertex that we've already explored. So any vertex that we end up exploring, it has to be a neighbor of 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 the original vertex or something. But that does basically give us a path and say that whatever we got to was reachable. The next thing to note is that a vertex W is not marked as visited unless it has already been explored, which is just the only way we mark things as visited is when we explore them. But finally, we should note that if W gets explored, well, we then look at all the neighbors of W, and either those neighbors have already been visited, in which case it means they've been explored at some point, or we end up exploring them. So in other words, if W gets explored, all of its neighbors also get explored. So to finish things, suppose that we have some vertex U that is reachable from V. That means that we've got a path from V going up to U. And if we actually explored everything along this path, we'd be done, because we would have explored U at some point. So let's assume that we don't. Assume that W is actually the furthest thing along this path that we've explored. However, by what we had on the previous slide, if you explore a vertex, you also explore all of its neighbors. So the next vertex Z along this path must also be explored. And so this is a contradiction. This says the only way this can work is if we've actually explored every vertex along the path, but that means we've explored U, which is good. Okay, so this explore algorithm is actually really great if we just want to find the vertices that are reachable from a given one. But sometimes you want to do a little bit more. You actually want to find all the vertices of the graph G, not just those coming from a given one. So for this, we're going to use a slightly more complicated algorithm called depth-first search. And for this, what we do is the following. First, we mark everything as unvisited. Then, for each vertex in the graph, if it has not yet been visited, we explore that vertex. So to look at an example on this graph, we find an unvisited vertex, say that one, and we explore it. So we find a neighbor and another neighbor, and then we pop back up the stack and then find something adjacent to our original vertex and come back. And now we're done exploring that first vertex. So now we look for a new vertex we've never visited before, like say that one. We explore its neighbor, come back. We're done exploring that guy. We find a new vertex that we haven't visited, that one. We explore its neighbor and his neighbor, and then come back. And now that we've actually visited all the vertices, only now do we sort of wrap up and conclude our algorithm. So to analyze the runtime of this algorithm, we have to note a few things. Firstly, whenever we explore a vertex, we immediately mark it as being visited. That's the first thing that we do. The next thing to note is that no vertex ever gets explored if it's already been visited. In fact, if you look at every time we make an explore as even a recursive call, then we always first check if it has not been visited, then we explore it. And this means that no vertex gets explored more than once. In fact, this means that each vertex gets explored exactly once, because the outer loop in the DFS explores every vertex if it hasn't already been visited. So, but each vertex in our graph gets explored exactly once. But for each vertex, when we explore it, there's this inner loop where we have to check all neighbors of that vertex. And so we have to do work for each neighbor of each vertex. And so we have to do work proportional to the total number of neighbors over all vertices. And that's proportional to the number of edges. Because each edge connecting A and B says that A is a neighbor of B and that B is a neighbor of A, so it contributes to sort of two neighbors. But the total amount of work is still O of the number of edges. So the total work, we do O of 1 work per vertex and O of 1 work per edge. And the total runtime is O of size of V plus size of E, a nice linear time algorithm. So that is depth-first search. Next time we're going to talk a little bit more about reachability in graphs and give some more applications of this algorithm. So I'll see you then.